Okay, here we go to the next part of the problem. This one involves some calculations. We've got in an experiment 40 mLs of 0.25 molar, that's our hypochlorous acid, is placed in a flask. We put it into a flask, then we get a burette, and we add some sodium hydroxide to it that we had in that previous equation. We add 14 mLs, and here we've got a concentration 0.435 molar sodium hydroxide. Calculate the amount of sodium hydroxide in the 14 mLs of 0.435 molar sodium hydroxide. Oh, this is a pretty straightforward problem. Very often, buried in FRQs, there'll be a simple question like this, where you can do something that you know pretty easily and just quickly fire out an answer and get a quick point. So don't give up on an FRQ if you don't know the first couple of things. Buried in it will be something that you can easily do. And of course, you know this. Concentration times volume will end up giving you moles, the amount. This is just like we know that if you take grams and divide it by molar mass, we get the amount. This is one of the equations that by now should be second nature to you. So let's do the calculation. I'm going to take and look here. I'm dealing with sodium hydroxide, so 14 mLs of 0.435 molar. Of course, we know that 0.435 molar means moles per liter. I mean, that's an automatic again. This M is an abbreviation. Moles per liter. We have 6.02 times 10 to the 23 of these hydroxide polyatomic ions times 0.435 in a liter. Quite a few little hydroxides floating around. And we multiply that times the volume. Now you say, wait a second, you've got liters here and milliliters here. Fine. That's great. I can do that. I can cancel out the liters and liters, and I get M moles millis. So I could just keep that unit just like this. There we go. 6.09 millimoles of hydroxide. The graders know what M stands for as a prefix. They know that stands for times 10 to the negative 3. Now, if you want, you can write times 10 to the negative 3. That's a pain in the neck. And you should be very comfortable in using millimoles. Don't forget your graders who grade AP exams. They're chemistry teachers who know what they're doing. In fact, they might even prefer the millimoles. Seeing this times 10 to the 3 over and over and over again will be boring. So, okay, we got one quick point. If you didn't have time to do an entire problem, you could have easily done this problem with your basic knowledge that you got back in chapter 4. Next, calculate the amount in moles or millimoles of the hypochlorite ion and the acid in the flask after the NaOH has been added. Okay, this is a tougher problem. This one's probably going to be worth 2 points. One of the points will be finding out how much hypochlorous acid was put in there, which is just like this concentration times volume. And we can just do that pretty quickly. Same basic idea, 0.25 moles per liter times our 40 mLs of volume. And you probably won't need a calculator for this one because that's 0.25 is a quarter times 40, 10 millimoles of HOCl. That was in the flask, but not for long because the sodium hydroxide reacted with it. Go back and look and you'll see that equation that the two react with one another. So now is time for an ice chart. Oh, I love ice charts. Now we're going to keep the amounts in millimoles because I don't want to type in times 10 to all the time. This is going to make things easier, and this is why I love millimoles. Here's our reaction. We've got our 10 millimoles of HOCl that we had in the flask. We dump in 6.09 millimoles of hydroxide ion. Arrow. Completely react to make water and our hypochlorite that's so happy as bleach. And here we go. Initially, that's what we start with. Arrow. It's going to change. Don't have to worry about an equilibrium here in terms of a Ks or anything else. This is 100%. And obviously, this 6.09 is going to react completely. There's 10 here, more than we need. We haven't reached the end point or the equimolar part. So we end up making hypochlorite ion. In fact, that's really how they get the hypochlorite in that bleach because the sodium hypochlorite is just so unstable. And here's what we have at the end, which will make an equilibrium, and I'll deal with equilibrium later. This answers our question. Calculate the amount of HOCl. Here's HOCl. Afterwards, here it is, 3.91 left. We have a little bit of this acid left, but our hydroxide's gone. It's completely gone. We didn't have enough of it. We didn't have any excess. But it went for good cause because it made some of our hypochlorite. Our second part of the answer, we're set. We got this problem taken care of.